In classical mechanics, an object's location and velocity dictate its future with precision. If initial conditions are known, a particle hits its target every time. This reality is mapped as a single point in phase space. The blue dot sits at an exact coordinate, x0, and a matching momentum, p0. That point fixes the object's position and momentum simultaneously. Knowing the point means knowing both properties perfectly. Quantum mechanics reveals a physical state cannot be compressed into a single point. A state with definite position appears as a narrow spike, but its momentum is completely spread. Conversely, a state with definite momentum becomes an endless wave, leaving the particle spatially undefined. These two physical descriptions are mutually exclusive. No single quantum state can possess a definite location and speed at the same time. This lack of a localized point forces a transition in how we define measurement. If the properties don't exist as definite values to begin with, the classical definition of a trajectory loses its meaning. To find where these properties actually go, we have to upgrade physical variables into Hermitian operators, mathematical tools that act upon the wave function to extract data. The Heisenberg uncertainty principle is often explained as a mechanical disturbance. Measuring an electron supposedly requires bouncing a photon off it, physically deflecting its path. While measurement does cause a disturbance, this observer effect model is a flawed explanation for the uncertainty principle. Uncertainty is a geometric theorem built into the operators themselves. It functions as a rigid law of nature, existing before any measurement is attempted. If a particle is smeared out over space, we need a way to determine what our laboratory instruments will actually record. We calculate the expectation value, the statistical average we would see if we measured identical systems thousands of times. This is a probability distribution. The blue shaded region represents the likelihood of finding the particle at different positions. The expectation value for position is the centroid, or balance point. We weight every possible position by its probability, summing them together to find the average. For position, this is a matter of simple multiplication. But calculating this same centroid for momentum is more complex, because our wave function is currently mapped in position space. The expectation value bridge converts these spread-out waves into the hard numbers we read on laboratory dials. Position and momentum exist in conjugate spaces. To see how momentum behaves, we have to look at how the wave function changes across the x-axis. The quantum state exists in two simultaneous representations, position space and momentum space. In the position domain, the position operator acts simply by multiplying the wave function. A Fourier transform provides the mathematical translation between these two spaces. Because of the Fourier relationship, the momentum operator in position space must take the spatial derivative of the wave function. Momentum is formally defined as negative I h bar times the partial derivative with respect to x. Multiplication in one domain requires differentiation in the other. This duality is the engine that generates all quantum incompatibility. We can now test what happens mathematically if we try to measure position and then momentum, versus momentum and then position. Physicists use a tool called the commutator to check if the order of these operations changes the final result. The commutator is the difference between measuring momentum first, then position, versus position first, then momentum. When we apply the derivative to the product of x and the wave function, the product rule of calculus expands the result into two terms. One is the original wave function, the other is x times the derivative. Because the first sequence only yields one of those terms, the subtraction leaves a single remainder of I h bar. The order of operations changes the outcome. This remainder exists solely because of the rules of calculus. It is an algebraic fact that has nothing to do with the quality of the measurement tool. Because these operators fundamentally refuse to commute, it is mathematically impossible for a state to possess simultaneous precise values for both. The non-zero commutator binds the statistical spread of position and momentum together into a permanent trade-off. This relationship is governed by the Kennard-Robertson bound, which defines the physical floor of nature. We can map this trade-off on a log-log plot. Every possible quantum state must exist somewhere on this coordinate system. The solid blue line marks the boundary where the uncertainty product equals h bar over 2. The shaded region below the line is forbidden by the laws of physics. No state, no matter how it is prepared, can ever cross this boundary. Every physical system must find a place to exist on or above this line, representing the most precise configuration nature allows. The Robertson boundary acts as the ultimate constraint on information, derived not from measurement limitations, but from the geometric requirements of operator algebra. By plotting specific systems, we can see how they negotiate this universal limit. The green circle represents a free particle Gaussian wave packet. This is a minimum uncertainty state. It sits flush against the boundary, meaning it saturates the bound with a perfect ratio of 1.000. The gold square represents a particle trapped in an infinite square well. The geometric confinement of the walls increases the total uncertainty, placing the state higher on the graph. Increasing the energy of the system moves the state further away from the boundary. We have traced the path from a classical point in space to a probability distribution, and finally to a mathematical proof that order of operations matters. The non-commutative nature of position and momentum operators dictates the structure of reality. Uncertainty exists because the operators themselves create the boundaries we observe.